Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh. Allahumma aftah alayna hikmataka wanshur alayna min khazaini rahmatika ya arhamar rahimin. Alright, so today we will continue to learn about time domain analysis. This is the third part, which is the last part. Alright, so previously we have learned about what is linear time invariant continuous system. Alright, so to know the total response of this system, basically we have to know the zero input response and also the zero state response. Alright, the total of this response will measure the total response of an LTIC system. Okay, in the zero input response, we learn about how to calculate the response by assume the input is zero, but there is initial condition. But for the zero state response, we assume that the initial condition is equivalent to zero. Alright, and using the unit impulse response, we also can measure the zero state response. Alright, the last part is about the convolutional integral, which we are currently learning. Okay, and then we will do conclusion. Okay, so for let's just recap what shall we do with this convolutional integral. Basically, there will be two signals, xt and ht. So the second one, okay, usually the ht we will rotate. Okay, so it will become h minus tau. Okay, so but before that we have to change this t, both of the equation with tau exists. Okay, and then the second equation we rotate at tau equal to 0 exists, so now become h minus tau, and then we shift it by a constant t. Okay, just name it constant t because we want to create an equation, mathematical equation, so we shift it by t. And then after that we multiply the xt, this is multiplication, xt and ht, but ht with the flip and shifted version. And then how to calculate the area under this product, we use this integration technique. Okay, and then we must ensure that we cover all regions or all parts of the equation, so we will divide into specific region, and then we repeat this step to know what is the condition of the yt, the output of this convolution integral. Okay, I've also shared you some example last chapter, but this one, let's see, this ft is having these equations. So what is this type of equation? It's a t but minus, right? Alright, and then shifted by 2. Okay, here. And then this is a rectangular with the size of 4. Right, so we want to convolve these two equations. So first, the step 1 is you have to change the t with a tau, right? And then we choose this one for easier flip and shift. So if we flip this or rotate it, it will become the same, and then we slide g tau. Okay, slide to the left first. Okay, so now it will be overlap like this. Okay, in the figure. Then we divide all region that is connected to the equations. Okay, so for the first region, t less than minus 2, okay, these functions do not overlap because the first function only exists here. Okay, so the area under this product is 0, right? So from minus 2, somewhere here, to 0, okay? So some of it will be overlap. So what we want to do now is we put a variable, or we put some limitation here to 2t. Okay, sorry. So 2 plus t will be, this is 0, okay. So we want to know what is the area under this one. Alright, so from 0 to 2 plus t. The limit is 0, 2 plus 3. And then we want to multiply the first equation and the second equation. This is the ft and this is the gt. Okay, or g tau. Okay, this is ft, f tau. Okay, same here also tau. Yeah. And then when we integrate, so 3 is constant, we put it outside. So to g tau, d tau, so minus tau over tau squared over 2 plus 2 tau. And then when you substitute the tau with 0 and 2 plus t, you will get this answer. So basically the area under here is minus 3t squared divided 2 plus 6. Okay, for the second region. And then for the third region, which is from 0 to 2 here, okay, we want to know what is the area under here. So we put a limit from 0 to 2, okay, and then we integrate. Again, the equation is the same, just the number or limit is different because just now we want to put a t for a variable, and then we got 6 since there is no t here. Okay, from 2 to 4, okay, from 2 to 4 somewhere here. So the part of GT and FT is overlap. So the calculation is same with minus 2 and 0. Because we have put the 2 plus t to 4, right? And then from t larger than 4 is not overlap, so the product is 0. Alright, so for here, the conclusion of the YT after we divide into 5 region, okay? So the first is 0, and then the second one, 0 to 2 plus t, and then 0 to 2 here, and then here is t plus 2 plus t to 4, okay, here, and then this is larger than 4. Okay, so when we divide, so first region, okay, second region, third region, fourth region, fifth region. Okay, 1, 2, 3, 4, 5. Alright, so let's say we check this second signal. If the first signal is E minus T and the second one is E minus 2T. Okay, so both are exponential. So the E minus 2T, which is HT, we put it as the second equation. So we shall rotate and shift this function. Okay, when we rotate, this is the H minus tau. Okay, so then we shift. Okay, when we shift, we check from the left side first. Okay, and then we integrate part by part, and then we move a little bit to the right, so they will, okay, so for this part basically they are not overlap, so 0. So the second part overlap, so we put integration with a value there, and then we start to integrate. Okay, this is the second region, yeah, 0 to t. Okay, so this is the YT, the output. Why we put UT? Because we want to tell that it exists only after t larger than 0. Okay, so that is the function of UT. Okay, so this is the derivation. If you check in the table, if you multiply a UT, convolve, okay, convolve with a UT, and then this is how do they derive. So UT convolve with UT, we will get TUT, okay, and then E minus AT UT convolve with e minus at ut, which is also available in the table. So you will get this answer. Okay, so this is how do they the derivation. Same goes here. Alright, so again what we should do to do this convolution integral. Okay, as I mentioned, so we need to since it's a graphical method, so you have to do the graph or the equation, the shape of the equation, and then we change into tau. Okay, and then we reflect. Okay, and then we shift by t. Alright, we will shift the t to the left side first. Okay, move to the far left and then write the mathematical representations. So at that intermediate signal, we can call it as wt at tau. Okay, the variable is tau. And then change into several, move it to the right to get several region. Alright, so and then we integrate each of it. Okay, so this is another equation. For example, we have ut minus 1. Okay, how ut minus 1 looks like? Ut is like this, right? And but if ut minus 1 is like this, okay, so this is 1. And then ut minus 3 is here, but it's negative. Okay, so come up with this rectangular. Same goes to this one. Okay, ut start with 0 and start with 2 but shifted. Okay, so we want to convolve these two equation. So we will divide it into several interval or region, and then t minus 1 between 1 to 3, 3 to 5, and t less than 5. That means we have the first one, of course, equivalent to 0. Okay, because 0 multiplied by 1 is 0. Okay, and then the second one, we do the integration. Alright, so this is the first, second and third and fourth. So if you see that we put it in graphical method, so this is the first equation, and then this is the second equation. Alright, so when you multiply here, you get this intermediate equation, and then you shift to the right. Okay, and then you divide it into 4 region. Okay, so this one 0, this is equation t minus 1. Okay, if you check here, it will be t minus 1, and here is 5 minus t. Okay, and then this is 0. Okay, so we can also do this for the RC circuit. RC circuit usually is represented by an exponential because it will decays, right? So the xt is the input, where we have this rectangular or unit step u. Okay, so xt is here and ht is here. Okay, so this one have been flipped and shift. Okay, alright, so you will divide it into several region. Okay, the first region, first interval t less than 0, you will get it 0. Second interval, you integrate between 0 to t. Okay, so you have to having this t as a variable. Okay, and then the third interval, t minus 2. So integrate again the e between 0 to 2, and then the third interval 1, 2, 3. Okay, we have 3 interval. Okay, now we can see this is the graphical method. XT, second one HT, and then this is the YT. You combine. This is the first integral, second integral, and third integral. Okay. Alright, so this is another example. This is t minus 1, but you have a limit from 1 to 3. Why? Because we have this unit steps multiply with this equation. Okay, so there is a limit here, and then this is the second one, ht, represented by this graph. Okay, so you shift step by step, interval by interval, and then you will get this graph as an output. Okay, xt, yt, the first interval, second interval, third, and fourth. Alright, so now it's the type of system connections. Basically, we have the first one, which is parallel connected system. Okay, when we said about parallel, that means the system will give input to this summation box or adder parallelly or in the same time. Okay, so the total will be the first response H1T and the second one H2T. Okay, so the output will be H1T convolved with XT, which is this one. This is the XT input. Okay, plus the second one HT, H2T convolved with the input XT. We also have a cascaded system. Okay, if we have cascaded system, that means step by step. So the first one, H1T, will be convolved with H2T, but H1T and H2T will gonna have each of it input XT, so convolve with the input XT. Okay, and also there is a commutative property, which is more or less the same with the cascaded system. So also H2T convolved with H1T. Okay, so for a system to be connected, there is also a integration and differentiation. That means, for example, we have this is the response, and then we integrate, or we integrate first and then we check the response. Okay, either by convolution, integral. Okay, same also true for differentiation. Right, so usually xt, the input, is an impulse, and ht will be the impulse response of the system. Okay, then gt is the step response. Okay, so let us reflect back in the first class about the time domain analysis. We see that the total response will be equivalent to the zero input response plus the zero step response. Okay, so we know how to find the zero input response, and we know how to find the zero step response. Okay, so the zero input response, usually they will come up with a characteristic equations or characteristic modes. So for this one, for the first type, which is the we have one value of lambda and ck. Okay, it can be also multiple plus c and lambda and t. Okay, depends on the input, whether it real and imaginary, or the characteristic root is different or same. Alright, and then the zero step response is depend on the convolutional integral. Okay. Alright, so if we want to consider a system to be stable, we should see whether it's causal, linear and time invariant. Okay, so if we have this kind of system, we will assume the system is stable or in equilibrium state. Okay. If we want to check whether the system is stable or equilibrium, so it has to be in the zero state. So for the system to be zero states, that means we should check that if the first we check it's a zero state, and then we suddenly disturb it by a non-zero state, but that system will stable naturally evolves to zero. So that means the system can be a stable system. That means at the end it will goes to zero or in the equilibrium condition. Okay. Alright, so for the zero input response, usually the system is represent or shaped by a characteristic modes. Okay, the E lambda, C, E lambda, T. Alright, so the output of a stable system of zero input condition, it will be categorized as stable if the system will goes to zero as t goes to infinity, just like this one. So sooner or later, naturally it will goes to zero. So that is a stable system. Alright, so let's see this example. If we have a stable system, only if characteristic mode tend to zero at st goes to infinity. Okay, just like what I explained before. So when it goes to zero naturally, so this one is a stable system. Okay, but if a system goes without bound, okay, like this one, without bound, there is no limitation and doesn't goes to zero when it comes to infinity, so this is unstable system. Alright, but if the zero input response remains bounded, okay, like this one, it remains bounded, okay, until a certain value, okay, with a constant amplitude. So it has a constant amplitude, okay. So it doesn't mean like this, okay, sometimes goes down or up until grows unbounded. So this is marginally stable. Okay. That means it has a limit here, bounded, and only goes to certain amplitude. Okay, not more than that. Okay. Okay, let's see this example. For example, we have an input like this. Okay, and then the characteristic modes or the zero state response will become like this, approaching zero. Okay, so it is a stable system, or it grows but at the end it will reach zero, also at infinity, also stable. Okay, for this one the system will going bigger and bigger. Okay, so it's unstable, and this is also growth exponentially, also unstable. But this one, we consider this is a sinusoidal signal where it has a limit or bounded and only goes to certain amplitude, is a marginally stable. Right? So I think that's the end of this chapter. So with that, I will stop here and see you insyaAllah. Wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi taala wabarakatuh.